Hello, myself Shomrat Pal, and now I am going to present a topic on chopper. It's a kind of converter. Okay? Just like a rectifier circuit or like an inverter circuit, it is actually a converter. But in case of rectifier, which can convert AC in terms of DC, and in case of inverter, which can convert DC in terms of AC. But chopper itself a converter which can convert DC to DC. That is why the another name of the chopper is DC-DC converter. But how it works means, suppose we are giving some input and which is DC signal, but which is having the fixed magnitude with respect to time. After chopper circuit, the output which will produced by it, that is variable DC. That means chopper itself a converter which can convert fixed DC to variable DC by keeping some switching on and off topology. As we know, every converter or inverter circuit or chopper circuit which is depends on the switching frequency and switch. When the switch is on, then the voltage is appearing across load, and when the switch is off, then the no voltage is appearing across load. Suppose we are using a particular kind of topology, okay, in which suppose this is suppose T on time, okay, and this is suppose T off time. That means if we are applying the triggering pulse across the any switch, when the switch remains on, then it provide the output voltage, and when switch is remaining in off state, then no output voltage will be appearing across load. That means after averaging this kind of output voltage, we will get the different value of DC. That is why we can say in case of chopper, we are using fixed DC which will be converted in terms of variable DC. Okay. Now, actually choppers are two types. Step up chopper and step down chopper, just like a transformer. As well as one more thing I must say here, that is in industrial application, chopper is required to convert a fixed voltage DC source into a variable voltage DC source. It is also called DC-DC converter, just I told you before. A DC converter can be considered as DC equivalent to an AC transformer with a variable turns ratio. Like a transformer, it can be used to step down and step up a DC voltage source. It also can be used in regenerative braking of DC motors to return energy back into the supply. And this feature results is energy saving for transportation system with frequent stop. DC converter can be used in DC regulator, electric traction, trolley cranes, electric vehicles, switch mode power supply or SMPS, etc. And normally for converter circuit, whenever we are implemented some kind of switches, they can be BJT, they can be power MOSFET, GTO, IGBT, or any other switching device will be there. Actually, this selection of the switch depends on what type of application we are going to apply. If we require the high frequency switching, then the selection of the switch will be different. If we require the switch which can able to protect or block the maximum output voltage during off state, then the switch will be different. That is why basis of the application we can apply different kind of switch for chopper circuit. Here we are going to demonstrate the total topic by using thyristor, as the thyristor can provide the high switching frequency as well as the blocking voltage of the thyristor is high enough with respect to other switches during off state. That is why now we are going to demonstrate the two types of chopper, that is number one, that is step down chopper and step up chopper. So go through the first circuit, that is step down chopper. So this is a circuit diagram of step down chopper or basic principle which is focused through this circuit. Here see, we are using a chopper circuit in which we have applied one switch, maybe suppose high resistor is there and a resistive load is there. It can be resistive load as well as it can be RL or RLE load. Any type of load can be applied for the chopper circuit. So now we are going to demonstrate the working principle of the chopper. See, and in the right hand side we assumed two axes, that is output voltage and output current, which is taken from the load. Okay, now see, here we are using the DC supply and which is constant in magnitude, and we are giving some triggering pulse across the thyristor. When the thyristor will on, immediately the voltage will appear across the load. When the thyristor remaining off, no voltage is appearing across load during off state. Again the thyristor will on again, then the voltage will be appearing across load. So in this way, see the output voltage where the thyristor is on, this is the output voltage waveform, and the thyristor is off, no voltage is appearing across the load, and total time taken during on and off, which is called the total time taken, and it is a complete cycle. Okay. Similarly, as we are using the resistive load, as we know, in case of resistive load, voltage and current both are in same phase. That is why we can draw the output current waveform just similar to voltage. That is why this is the output current waveform, as resistive load is there, and the value of the output current, that is Vs by R. As the when switch is on, then the current starts flowing from source to load in this way, and voltage appearing across load is Vs. This is, and when the switch is off, then no voltage is appearing across load. That is why no voltage appearing across load. That is why this is the waveform of the output voltage and current. Now we are going to calculate the average value. Okay. One more thing is a chopping cycle. Depending on this, we are just demonstrate the operation. That is why this is not defined by omega t. This is defined by the only the time axis t. Okay. And one more thing is very important to understand. This ratio means the on time. This ratio means on time, that is t on, and the total cycle that which is defined by t, which is called duty cycle K, or somehow it can be represented by D. So duty cycle means, keep it in your mind, that is on time by total time. That means what? If we are increasing or decreasing the on time, that means the average voltage to the output should be increased or decreased. That is obviously applicable for the any drive control part or machine part. That means the machine speed will be increased or decreased respectively. That is why by changing duty cycle, we can change the any type of drive, we can control the drive speed. Okay. Now go through the calculation part. So in this case, we can say the average output voltage to the output terminal, suppose V average, that should be equal to number of peaks in the positive direction in a complete cycle, right? So in the complete cycle means T, how many peaks are there in the output voltage? That is 1. So we can say the output peaks, positive peaks, that is 1 divided by complete cycle defined by T, integration of confined region the particular peaks. Means this peaks is confined in which region? That will start from 0 and is ended over t on, right? That is why we can say the confined region is 0 to t on. And the expression is what? Voltage expression. Obviously, when the switch starts conducting, then the voltage is appearing across load. That means we can say VO must be equal to VS, right? With respect to time domain, that is TD. So this is the expression for to calculate the average output voltage. Okay. Now do the calculation part, and which is reflected on the next sheet. See here, right? So in this case, see it very carefully. The average output voltage VA, that is equal to 1 by T, just I told you before, 1 by T integration of 0 to integration of 0 to T on V0 dt, and V0 equal to Vs. That is why we can write 1 by T integration of 0 থেকে T1 Vs dt. After integrating, we will get the result, that is Vs by T, T upper limit T1 and lower limit T0. After simplification, we will get the result, that is T1 minus 0, that will give you only T1. So that means T1 by T Vs, right? That means we know 1 by T, that is actually frequency. So we can change the term, that is 1 by T equal to F. That means what? We can replace this part by F term here. Okay, that means 1 by T equal to F. Okay, fine. That is why we can simplify, that is 1, that is equal to F, that is equal to F into T on into Vs. So ultimately we will get the result, that is T on by T equal to K. We assume that is called duty cycle. Okay, so we can change the expression in this way, that is K into Vs. And similarly, we can calculate the average output current IA, that is resistive load, that means VA by R, that will give you K into Vs by R. So that is all about for the calculation of average output voltage and average output current. Now we should calculate the RMS value also. So this is the sheet in which we can explain the calculation of the RMS value. See, in this sheet, the calculation part is given. The RMS value, that is equal to root mean square. So that is why V0 square dt 0 to T1. So after simplification, we can mention the equation, that is 1 by T integration of 0 to T on Vs square it as V0 equal to Vs, right? After simplification, we will get the result, that is Va square T, T0 to T1 under root. As root means square, we are going to calculate the RMS value. So ultimately, we will get the RMS value, that is equal to, after simplification part, which is all steps are given over here, and ultimately we will get the result, that is root K Vs. Okay, in which K equal to duty cycle, and that is defined by T on by T. That means T1 can be maximum 2T. If we can switch on the switch, suppose we can switch on the device 0 to T, that is the maximum time on time, T on time. That means we can say T by T equal to, means T0 by T equal to 1. apart from this case, all the cases, suppose 0 to t, it will give you less than 1. That means we can say duty cycle k always less than 1. As we have got the result root k vs, all the cases, if vs is multiplied by any term which is less than 1, that means it will give you the less amount of output voltage with respect to vs. So we can conclude that the output voltage VO must be less than V in or input voltage. That is why this is called step down chopper. Understand? So this is called step down chopper. Now see, the duty cycle K can be varied from 0 to 1, just I told you before, by varying on T and F. Therefore the output voltage V0 can be varied from 0 to Vs, obviously. So by controlling K, and power flow can be controlled. That is why you can control the speed of any machine for drive application. The controlled strategy are two types, that is pulse width modulation or constant frequency operation. Number 2 is frequency modulation or variable frequency operation. That means by controlling this duty cycle, we will get the two types of operation for step down chopper, that is pulse width modulation and frequency modulation. In the first case, we can say that is the control frequency operation, and there is constant frequency operation and variable frequency operation. So please try to understand what the meaning of these two terms. That will be reflected on the next slide first. See, it's a very interesting part. First, the concept is pulse width modulation. This is the first concept. Suppose we are giving the triggering pulse to the switch such a manner through which we will get this kind of output voltage, in which this is the on time and this is off time, and total cycle, that is on plus off, which will give you this one. Suppose we can change the pulse width. See, here the pulse width was this one. Now the pulse width is increased with respect to first one. That means what? During the same duration, means the time t, the pulse width has changed, keeping, and as well as the turn of time has changed. That means what? We are not changing the frequency, the time duration remaining same, but we can change the pulse width to the output. That means what? The average, by changing the pulse width or by changing the duty cycle, we can change the average output voltage. Right? So that is why this is called pulse width modulation or constant frequency, as the frequency is constant for the both purpose. This is the operation. Now think about the variable frequency operation, which is mentioned over here, or frequency modulation. Frequency modulation means we are changing the frequency. First was the pulse width modulation. That means we have changed the pulse width, not frequency. Here we are going to change the frequency, but maybe the pulse width during on and off remaining same. That is why we consider the two types of operation. Number 1, that is on time constant, or number 2, off time constant. But the frequency must be changed. So what happened? See the first output voltage V out, where this is the on time and this is suppose off time, and this is the frequency, that is F equal to 1 by T. And we are changing, means we are changing the triggering pulse to the switch during the conversion operation or during chopping operation. That means keeping time on constant same, but we can change the off time here and here. In the first case, the off time was this much. In this case, the off time is this one. That means keeping turn on, or the on time constant, we are changing the off time. That means what? Ultimately we will get in this particular cycle, now we will achieve the 3 times of peaks or pulse are here. That means we can say we have changed the frequency, or total time has changed. That means that means we can say the time duration has changed, means the frequency has changed. So if we consider the frequency just like the before, then we will get, in the first case, one pulse is there, in which we will get the 3 pulses. That means this is called the frequency operation or frequency modulation. This is keeping on time constant. Now for off time constant, what happened? See, this is the off time, okay? That is why, and this is on time. That is why the total frequency 1 by T equal to this one, right? Suppose off time constant remaining constant, this is the off time remaining constant, but we are changing the on time from this much to this much. That means what? As we know, off plus on, which will give you the total cycle, that means the cycle has changed or frequency has changed. So that is why this is called the frequency modulation. So ultimately we will get what? That is, in this particular frequency where we had achieved the 2 number of pulses, here we will get the 1 pulse. That is why this is called the frequency modulation. Okay, so this is all about for the step down choppers, and with respect to variable duty cycle, how the output voltage can change during variable frequency operation or frequency modulation operation, as well as for constant frequency operation or pulse width modulation. Okay, so this is all about for the step down chopper. Now one more interesting part, that is step up chopper. As we know, this is working as just like similar to a AC transformer. During that, by changing the trans ratio to the secondary part, the transformer can act as somehow for step up and step down chopper. Step down, that is step down transformer. Similar here, we are changing the circuit, and see the circuit very carefully. Is a very interesting part, as we are going to introduce the inductor part here. Okay, and this is the circuit diagram for the step up chopper, where we are using the switch or thyristor across the voltage source, not just similar to before in series of voltage source, and we are connecting a inductor series with respect to supply, and diode is there to block the voltage, maybe some charging or discharging path. Okay, so it can cover 2 mode operation actually. Mode 1, when the switch remaining closed, then the current starts flowing in this direction. One more operation, the another mode, when the switch remaining open, then the current starts flowing in this direction, right? Then what happen if we consider this type of 2 mode operation? So first circuit, here we declare the circuit for charging of the inductor when the switch remaining closed. When the switch is closed, then the switch is behaving like a closed circuit. Then easily the current starts flowing through this circuit in this way. Then the inductor gets charged to a value of supply voltage Vs. And the polarity of the inductor is, this part is positive and this is negative part. Okay, and so this is, and that is why we can say this is the mode of operation in which the inductor stores energy in it. Now consider the second mode operation where the switch is opened. That means it is behaving like an open circuit. That is why now now as the property of the inductor, when the inductor was completely charged, then it has make the polarity just due to the back EMF concept, just opposite of original voltage source. When the inductor is fully charged, then when the inductor try to discharge right now, then the polarity should be changed. That is why the inductor polarity has changed. Once the inductor polarity has changed, as well as the switch was open, that is why the actual voltage, that is inductor stored energy, that is defined by L di dt, and the supply voltage Vs, which is summing in nature, that is why total voltage, that is Vs plus L di dt, that should be appears across the load as the current starts flowing in this direction, right? That is a total supply voltage Vs, Vs, which will be added the energy stored inside the inductor L di dt. Okay, so that means what? That means now VO, the result of VO is what? That the VO that can be defined, the VO that can be defined by the voltage coming from input voltage Vs plus L di dt. That means what? L di dt plus Vs. That means what? That is the actual voltage for VO. That means we can say VO must be greater than Vs. So that is why we can say this is step up chopper, as the output voltage is greater than input voltage. Just similar like a step up transformer. That is why this is called step up chopper. Now similarly, just like before, we are going to calculate the all average value and the RMS value during step up chopper. Now first we are explaining the waveform from the circuit. See, when the switch is on during first mode operation, then what? Inductor gets charged. That means inductor current is gradually increases from its low value to high value during on state, right? When the inductor gets fully charged during off state, then the inductor starts discharging, so during off state. So this is the waveform for the inductor current. Due to presence of inductor current, that is the waveform for inductor current. Similarly, we know the voltage. In case of the voltage, that is when the switch was on, then the inductor starts storing energy inside it, but the no voltage is appearing to the supply. That is why no voltage appears to the no voltage is appearing to the load. When the switch was off, then the inductor stored energy with some of the supply voltages appearing across the load. That is why this is the output voltage. Okay, got my point? So we can say the I0 that must be equal to, there is a no concept of I0 at the switch was on, then the inductor was charged, no current was transmitted to the output side, but the inductor, when the switch was off, when the inductor starts discharging, then the current starts flowing to the load. That is why this current should follow the inductor discharging current. Okay, so this is the waveform for output voltage and output current. Here we are using the constant DC, but ultimately output voltage is pulsating DC. That means the average should be decreased with respect to the input, or we can vary the output voltage, and this is the output current. Okay, now go to the calculation part. That means see the waveform very carefully. That means if the inductor or the total system is lossless, that means inductor stored energy during this time t on and inductor discharge energy during the time t off, both will be same. This concept is applicable to calculate the average value and the output voltage. Now see, go through the topic, that is to calculate the average value. The approach is something different, not similar to the previous one. See, the energy input to the inductor from the source during the on time, that means voltage across the inductor into average current through the inductor and during the time duration. That is why go to the first one. See, I recall the previous the circuit. Okay, this is the circuit. See, I just want to recall you. When the inductor starts storing energy, okay, means inductor stored energy, then the switch was off during off state, then the inductor energy has stored here, right? Then the switch was on during t on. That means then the current was gradually increases, which is defined by the waveform, that is del I. Suppose I1 to I2 during this time, gradually increases, and after that the gradually decreases, suppose I2 again to I1, right? That means during T1 what happened? The current is gradually increases I1 to I2. So the average current should be equal to I1 plus I2 by 2, right? Okay, and the time duration is T1. Okay, and this is the energy stored. And during of what? Again the current falls from I2 to I1. During T of, again the average output current will be T2 plus T1 by 2. Similar thing I have done in the expression. See, that means we can say, okay, we can say the energy stored during on. And in this particular case, when the switch was on, no relation source to load. That is why the total voltage appearing across the inductor, that is only Vs, and inductor average current I1 plus I2 by 2 during time, that is T1. So we can say the energy in or energy stored during on time, this is the expression. Similarly, during off, we can say again, off time means what? When the switch was off, that means then the voltage appears to the load, that is Vs plus L di dt. That means in this particular duration, we can say the voltage appearing across the inductor, that is V0 minus Vs, right? So that is the means potential difference across the inductor, output voltage minus input voltage, as the current is easily conducted from source to load. That is why V0 minus Vs. And similarly, we can say again the current falls, that is I2 to I1, that is the average current, that is I1 plus I2 by 2 during T off. So this is the energy output during off time. So as the system is lossless, we consider both equation will be same because of inductor stored energy during on and inductor stored energy during off, both will be same. That is why we can write, that is Vs, inductor stored energy I1 plus I2 by 2 T on, that should be equal to V0 minus Vs I1 plus I2 by 2 T2. So just go through the simplification part. That is Vs equal to, we can say, that is Vs equal to which one? That is Vs into T1 equal to Vs minus 0 by this one. Similarly, we can again simplify the equation Vs equal to T1 plus T off equal to V0 T off, right? Why we are changing the equation like this one? As we know, T1 plus T off equal to T total time. That is why Vs into T equal to V0 T off. So further simplification, we will get that T by T off, right? And T off means T minus T1. That means we can change the expression, that is 1 by 1 minus T1 plus T. Why we are changing the equation? As we know, T1 by T, which is called duty cycle, and which can be replaced by K term. That is why we can say the output voltage, the final expression is V0 equal to Vs 1 by 1 minus K. And as we know, it's a very important part, the duty cycle K always less than 1. That means what? That means 1 by 1 minus K. That means this denominator part must be less. That means the total part must be greater than with respect to we can conclude from the equation. That means we can say if K greater than less than 1, that means the expression which will give you the more voltage with respect to V0. That means Vs multiplied by this term, which will give you, suppose, any result V0 which must be greater than V in with respect to supply voltage. That is why we can say this is a step up chopper. Okay. As we know, is well defined by here, the average output voltage across the load can be stepped up by using a stepped up. So we can say the stepped up the duty cycle depending on the duty cycle. That means if K equal to 0, that means V0 equal to Vs is the minimum value. If K equal to 1, the maximum value, then V0 will be infinite because K is the part of denominator, which will give the infinite voltage. That means all the cases by satisfying the condition k equal to 0 to 1, it will provide you the voltage Vs to infinite. That means what is a step up chopper. Okay, thank you.